Evet, değerli katılımcılar, kongremizin son gününde davetli konuşmacımız Profesör Doktor Mehmet Emir Koksal, 19 Mayıs Üniversitesi Matematik bölümünde görev yapıyor. Şu an ziyaretçi profesör olarak Hollanda'da Twente Üniversitesi değil mi hocam?
Evet.
University of Twente'de çalışmalarına devam ediyor. Başarılı projeleri imza atmış bir hocamız. Aynı zamanda yakın zamanda haberlerden de gördük hocam. Sporcu kimliğinizde ön plana çıkmış yani.
Estağfurullah.
Başarılarınızın devamını temenni ediyoruz. Eğer sizin için de uygunsa başlayabiliriz.
Başlayalım. Uygun.
Tamam hocam.
The title of my talk is Commutativity and its use for optimizing performance of cascade connected systems. This is the plan of my presentation. As a first, I will define commutativity. Next, I will give the explicit result for continuous time varying systems. And then I will give the commutative pairs of some famous second order continuous time varying differential systems. Next, I will talk about the commutativity conditions of Euler and feedback systems. And then I will define the concepts of decomposition and transitivity properties of commutativity. Next, I will give some results for the commutativity of discrete time varying systems. Then, after talking about some benefits of the commutativity, I will end up my presentation by giving some open problems. Here you see the simple block diagram representation of a system. If the output function of the system A is equal to the input function of the next system B, then A and AB are said to be cascade connected systems of A and B. BA is also a cascade connected system of the system B and A. Continuous time varying systems are described by differential equations, and discrete time varying systems are described by difference equations. Cascade connected systems are used in many engineering applications. The realization of many engineering systems consists of simple order cascade connected systems, which is very important in the design of electrical and electronic systems. Although the order of the connection of the system mainly depends on special design approach, when the stability, sensitivity, robustness, linearity, disturbance effects are considered, the change of the order of the connection without changing the main function of the total system may lead positive results. Therefore, the commutativity is very important from practical points of view. Here, A is a low-pass filter, B is a high-pass filter. A buffer is added into the interconnection of the system A and B. The cascade connection of the system AB is a band-pass filter. BA is also a band-pass filter. This subject was studied for the first time in 1977 by Marshall, and he proved that a linear time varying system can be commutative with only another linear time varying systems. And he proved the commutativity conditions for the first order continuous time varying systems. After that, commutativity conditions for the second, third, and fourth order continuous time varying systems were studied in 1982, 83, and 85, respectively. After a long period of time, fifth and sixth order systems were studied in 2011 and 2021, respectively. Even though there is a large cycle of work on the commutativity conditions of the continuous time varying systems, there are a few literature about the commutativity conditions of discrete time varying systems, which are studied in 2015 and 2019. for the second order and first order respectively. Here are the results for the explicit commutativity conditions for continuous time varying systems. This matrix expression must be satisfied for the commutativity of first order systems. These are the results for the commutativity of second order continuous time varying systems, which are expressed by matrix equation and by this expression written in the complete differential form. They are equivalent to each other. And this matrix expression must be satisfied for the commutativity of third order continuous time varying systems where the elements of the matrix are defined like this. And here is the result for the commutativity conditions of fourth order continuous time varying systems. And these are the results for the commutativity of fifth order continuous time varying systems where the elements of the matrix are defined like this. Unfortunately, commutativity conditions written in the complete differential form for third, fourth, and fifth order continuous time varying systems have not been obtained until this time. There are too many famous second order differential equations in the literature written in this form, and they can be classified according to the homogeneity and linearity properties as shown in this table. Using the commutativity conditions written in matrix form or written in the complete differential form, we can determine that these famous second order differential equations have a commutative pair or not. So this expression must be satisfied for the commutativity of second order differential equation. So, for example, a continuous time varying system described by Euler equations satisfied the expression. So, the expression written in this parenthesis must be a constant coefficient for the existence of the commutative pair of second order continuous time varying systems. So Euler equation always satisfies the commutativity conditions. So any second order continuous time varying system described by Euler equation has always a commutative pairs, and commutative pairs is described by these differential equations, and using the matrix equation we can find its commutative pairs. It's proven that Euler systems of order n and m are always commutative, and conditions of the cascade systems AB and BA have the same impulse response expressed as GAB and GBA, where the entiers of submatrix capital A12 and B12 calculated by these formulas. Here, sigma A is the feedback path gain and sigma B is the feedback path gain of the system B, and alpha A is the feed forward path gain and alpha B is the feed forward path gain. Let S be a linear time varying analog systems. A is obtained from S by constant feed-forward and feedback connection as shown in this figure. B is also obtained from S similarly. Then A and B are always commutative with these conditions. Decomposition is an important tool that is used in many differential systems for solving real engineering problems and improving the stability, sensitivity, robustness of a system. It involves breaking down a high-order linear system into the lower-order commutative pairs and helps in breaking down complex problems into more simpler parts. The reduced parts can be easily solved and analyzed separately as they are easier to work with. If a problem is not reduced, then it's very difficult to solve in many cases. So that concept was studied for the first time in 2016, and second-order continuous time-varying systems was reduced to the cascade connection of the two first-order commutative pairs. A linear time-varying system can be decomposed as the cascade connection of two commutative subsystems, and the decomposition conditions and form are given by this theorem for second-order relaxed subsystem. For non-relaxed systems, we have two more conditions, and corollary 1 and corollary 2 give additional conditions of the commutativity for non-relaxed systems. Now, as an example, we consider this second-order differential equation describes system C, and it can be decomposed as the cascade connection of the two first-order systems A and B. Now, for subsystems A and B to be likely stable, K1 and K0 should be chosen on the blue region. The dashed line shows the location of K1 and K0 for non-zero initial conditions. For two different sets of K1, K0 values in the S region, we obtain the outputs of AB and BA, the compositions shown in this figure. The response of C is equal to the response of AB and BA. After that, the decomposition of third-order continuous time-varying systems as the cascaded connection of the first and second-order cascade connected systems was studied in 2019. And the coefficients of the system C can be found by this formula given in theorem 4. And these are additional conditions for non-relaxed systems. And the coefficients of A system B can be found by using the coefficient of the main system C. And this theorem 5 gives the formula of finding the coefficients of system A and B. Now, as an example, we consider a third order linear differential equations, and it can be decomposed as the cascade connection of the first and second order differential equations. When initial conditions are not zero, the details of initial conditions of systems are given as described in this slide. When conditions are satisfied, the response of C is the same with the response of AB, and it's also same with the response of BA. When some of the decomposition conditions are spoiled, the responses get difference from that of the original system C. For example, as you see from this figure, the response of C1 is different than the response of AB3. Now I will give the definition of the transitivity property of the commutativity. Logically, transitivity is a property of a binary relation such that whenever one element is related to a second element and the second element is related to the third element, then the first element is also related to the third element. Let A, B, C be dynamical systems described by linear time-varying differential equation with their special input-output variables. Orders of complexity, if A and B are commutative among themselves, further B is commutative among themselves, what can it be said about the commutativity of system A and C? If A and C are also commutative among themselves, this property is called the transitivity property of commutativity. In other words, commutativity is a transitivity relation. So AB is same BA, BC is same CB, so ACA is same with AC. Theorem 6 expresses that the transitivity property of first-order linear time-varying analog systems always hold with zero and non-zero initial conditions. Let A and B have impulse responses HA and HB. The commutativity, the cascade connections of AB and BA have these impulse responses HAB and HBA. And theorem 7 expresses necessary and sufficient conditions for the commutativity of relaxed subsystems A and B in terms of their impulse responses. So, for the proofs of the commutativity of system C and A, that is the transitive property of commutativity, it is required to show that HCA is equal to HAC, which is equivalent to this formula. Let ABC be the first order initially relaxed linear time-varying system described by these differential equations, and their impulse responses are defined like these, where FA, FB, and FC are defined like these. Now, we can obtain that the response the impulse response of AB is equal to the impulse response of BA. And also we can show that HBC is equal to HCB, then HCA is equal to HAC. And this proves that A and C are also commutative, so that the transitivity property of commutativity holds. When we consider the commutativity of two second-order linear analog systems, A and B, is described in equations 6.1 and 6.2 respectively, it is well known that the system B must be expressible as in the equation 6.3, where Ci are arbitrary constant. Now, we asked that question, how the coefficients of system A are expressed in terms of the system C of system B. The answer is given by equations in these slides. As you see, these conditions are similar to the previous conditions, and they are called as inverse commutativity conditions. The condition revealed that the arbitrary confidence are related as in 6.9, or inversely as in equation 6.10. And we summarize the result in the previous 3 slides by this theorem 8. And these are the remaining of the theorem. The mentioned inverse conditions are used to prove the transitivity property of the commutativity of second-order linear time-varying systems. This property is expressed by theorem 9 and theorem 10, this slide. To illustrate the validity of the results, we consider the system A, B, C described by these differential equations with the given initial conditions. Now, we assume the input function is equal to 40 sine 10 pi t. Then the simulations are done by MATLAB Simulink Toolbox with the fixed time step of 0.02. And as you see from figure 8, the response of AB is equal to the response of BA. And the response of BC is also equal to the response of CB. And the response of CA is equal to the response of AC. In the case of non-zero initial conditions. And also there So when we take the initial conditions arbitrarily, which do not satisfy the commutativity, then the response of AB is different than the response of BA. The response of BC is different than the response of CB, and the response of CA is different than the response of AC because of the fact that initial conditions spoils the commutativity conditions. So even though there is a large cycle of work on the commutativity conditions of continuous time-varying systems, there are a few literature about the commutativity conditions of discrete time-varying systems, even though the trend with the new technology is moving to the digital work from analog work. Especially in modern technology, most of the recent devices are produced for digital technology. Then the commutativity conditions for the second order discrete time varying systems were proved 6 years ago. And we assume the system A and B are described by these second order difference equations. So for the existence of the commutativity of second order discrete time varying systems, these equations must be satisfied. For the non-relaxed systems, these additional conditions must be satisfied among the initial conditions of the systems A and B. This is the remaining parts of the initial conditions. I want to mention that the necessary and sufficient conditions for the commutativity of second order discrete time varying systems described by these theorems are completely dissimilar from the commutativity conditions of continuous time varying systems. However, the commutativity conditions of the first order discrete time varying systems are similar to the commutativity conditions of the first order continuous time varying systems, as you see in theorem 14. And the commutativity conditions of the first order discrete time varying systems were obtained 3 years ago. And this is the example for the commutativity of first order discrete time varying systems, and we assume the systems A and B are described by these first order difference equations respectively. For the relaxed systems, the response of AB is the same with the response of BA, as you see from the black line. But for the arbitrary choosing of initial conditions which do not satisfy the additional initial conditions for the commutativity, response of AB is different than the response of BA, as shown in blue line and red line. And here, when a noise disturbance is added into the interconnection of the system A and B, for the noiseless case, the response of AB is same with the response of BA. But when a noise of 5 unit is added, the response of AB is different than the response of BA. And here, when there is no distortion, the response of AB is the same with the response of BA. But with the distortion, the response of AB is different than the response of BA, as shown in this slide. Now I want to talk about the benefits of the commutativity. Commutativity can be used for discrete communications, and this privacy can be increased with switching. Although the same signal is received on the receiver side, this signal is transferred in different form on the transmitting medium between A and B. This will puzzle the unauthorized people trying to reach the transmitted information. Consider a communication system as shown in this figure. In this figure, A and B represent commutative linear time varying systems so that both channels AB and BA produce the same output signal for any applied input signal. But the transferred signal from transmitter to receiver procedure in completely different shapes through the transmitting medium. Hence, this generates somewhat prevention against the infiltrator to stealing the secret information during transmission. To observe that both are switching alternatives from A to B and B to A shown in the figure 14a, where A and B are defined like these, yields the same output at the receiver side. And input signal is applied to the transmitter side. Let A and B defined by these second-order differential equations. As observed in this figure, the transmissions from A to B and from B to A yield the same output signal in spite of the same input-output pairs of switching AB and BA. The traveled signal proceed through the transmission medium are quite different. In figure 16, the same fact observed in the previous figure is seen to be valid for different input signal as well. The same fact observed in figure 15 and 16 are observed for a different example when the systems A and B are described by first-order differential equations. We see that in case of switching, the signals outputs from AB and BA are almost the same. So switching hardly spoils the commutativity. We see that the transmission signal in the transmission paths are completely different, even though the receiver sides of AB and BA are the same. And we see the same fact states for figure 18. And this graph shows the switching effect when the transmission is switched from AB to BA. We see that the switching does not influence the outputs effectively. So the outputs of AB and BA are almost the same in the case of switching as well. As seen in this figure, the switching disturbance disappear in a very short time. The transmitted signals traveling through the transmission medium between A and B are shown, and they are different in the case of switching. Power spectrum of transmitted signals show the difference of traveling signal from A to B and from B to A more clearly in this figure. Naturally, their power spectrums are also different as shown here. Here are some open problems for the further developments of the commutativity. And commutativity of third and higher order discrete time varying system can be studied. And also commutativity of fractional or non-linear continuous and discrete time varying systems can be studied, and also the composition and transitivity properties of high order continuous and discrete time varying system can be studied as a future work, and also more physical applications can be studied. And these are references. And thanks to TÜBİTAK, because most of the studies on the second order continuous time varying systems have been supported by the Scientific and Technological Research Council of Turkey under a project in which I have a role as a principal investigator. And that project has been awarded as a project performance worked by the Scientific and Technological Research Council of Turkey. And thanks to the chair, Professor Turgut Özseven, and all committees of this conference for the invitation. And thank you very much for your attention. Those who are interested deeply with this presentation could be contact with me by email.
Thank you for presentation. Is there any question? Okay,